Hi guys, Professor Burns here. We're going to take a look at section 4.3 where we're continuing to talk about how we can use the characteristic equation or the auxiliary equation to solve a homogeneous second order linear differential equation with constant coefficients. Make sure your cell phone is put away and you have your notes out and you're ready to pay attention for the next 10 minutes or so. Yesterday, in the previous lesson, we talked about what to do if you solve that characteristic equation and you get real solutions, either two distinct real solutions or a repeated root. Today, we're going to talk about what to do if you solve that characteristic equation and you end up with complex roots. And remember that when you solve a quadratic equation and you get complex roots, I know it's probably been a while since you've dealt with complex numbers, but when you do that, they always come in conjugate pairs. So let's go through the process here. Remember the characteristic equation, if you have a differential equation in this format, then it has this associated characteristic equation, AR squared plus BR plus C. If we solve that equation and we end up with complex conjugate roots, and we're going to call those alpha plus or minus beta I, then we know that y equals e to the alpha t cosine beta t and e to the alpha t sine beta t are going to be particular solutions. And just like in the previous section, we can combine those to get our general solution, and that becomes c1 e to the alpha t cosine of beta t plus c2 e to the alpha t sine of beta t. And that would give us the general solution to the original second order differential equation. So let's look at a couple of examples here and see how this works. Let's start with the simple harmonic equation, y double prime plus y equals 0. So notice it's equal to 0. That tells us we can use the auxiliary equation to solve it. So my auxiliary equation is going to be r squared plus 1, because note that a would be 1, b would be 0 in this case because there's no y prime term, and c would be 1 because of the y. So if we set that equal to 0, we get r squared equals negative 1 square root. Remember, when you take the square root, you got to do plus minus. So we get plus minus the square root of negative 1, which is just I. So my solutions are complex numbers. Notice that alpha in this case would be, alpha is the real part of the complex number. So alpha would be 0. Beta is the imaginary part, so in this case beta would just be 1. That's the coefficient on the I term. So when we put this together, my general solution becomes C1 times e to the alpha t, which is just 0 t, cosine of beta t. I'm just writing this out for emphasis, but we'll clean this up. C2 e to the 0 t again, sine of beta t, and of course that's going to be e to the 0, which is 1, so I end up with C1 times cosine of beta t plus C2 times sine of beta t. And that is going to be the general solution to the original differential equation. Let's do another example, and this is an initial value problem now. Notice that they've given us two pieces of information, that y of 0 is equal to 0 and y prime of 0 is equal to 2. So because the original differential equation is equal to 0, we know we can use the characteristic equation to solve it. So I'm going to go ahead and write out what that is. A would be 1, B would be 2, and C would also be 2. So we have r squared plus 2r plus 2 equals 0. This, notice, does not factor, so to solve this we have to use the quadratic formula. So r is going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And let's see, this is going to give me 4 minus 8, which gives me the square root of negative 4 over 2, which gives me negative 2 plus minus 2i over 2. And I'm going to simplify that a little bit because those can all divide out by 2. I get negative 1 plus or minus I. So notice from this, that means that alpha is equal to negative 1 and beta is equal to positive 1. So when we put this together using the format above, we wind up with a general solution that looks like this. Y of t is equal to C1 e to the negative t times cosine of t, because beta was 1, plus C2 e to the negative t sine of t, because beta was 1. So this would be the general solution if they asked us to find that. They want us to go a little bit further. This is an initial value problem, which means I need to find what those C values are. Now, in order to use these initial conditions, or at least the second one, the y prime condition, I have to find y prime. So if this is y, I can plug in 0, 0 and get an equation involving C1 and C2, but I also need to involve the derivative y prime in order to use the second initial condition. So let's go ahead and take the derivative. I'm going to factor out an e to the negative t here, and that leaves me with C1 cosine of t plus C2 sine of t. And that means that to find y prime, I'm going to use the product rule, so the derivative of the first times the second recopied. And then plus the derivative of the second, which is going to just be the derivative cosine, C1 cosine of t plus C2 sine of t. So that'll be, sorry, I didn't leave you a ton of room here. That'll be negative C1 sine of t. Let me erase some stuff here just so we have a little bit more room. And then the derivative of sine would be positive cosine. So that would be, let's see, plus C2 cosine of t, and then times the first recopied, which was e to the negative t. So this is not a pretty equation, but we can work with it. Let's go ahead and put in the information they gave us. I'm going to start with 0, 0. Now that went with the original y equation, so I'm going to plug that into the y equation here. 0 is equal to e to the 0 power times C1 cosine of 0 plus C2 sine of 0. Sine of 0, of course, is 0, so that goes away. E to the 0, of course, is 1. Cosine of 0 is 1, so what does that mean? That means that C1 is equal to 0. Now I have C1, I can find C2 by substituting that into the first derivative equation. So the first derivative information is here, and that means that 2 is equal to negative, I'm plugging it in right here, e to the 0 power times C1, which was 0, plus C2 sine of 0, so those are going to go away, plus, I'm going to write this e term first, e to the 0 power times 0 for that first term, plus C2 times cosine of 0. So this all zeroes out, and then here cosine of 0 is 1, e to the 0 is 1, so I have c sub 2 times 1, so just c sub 2 equals 2 is what I'm getting. All right, so then what does my particular solution look like? My initial value problem is the particular solution using this initial value information that they gave us. So it's going to be y of t is equal to C1, which was 0, so that entire, here, let me highlight what I'm working with. I'm working with this equation right here. That entire first term is going to go away because C1 happened to be 0, and C2 was 2. So it's going to be 2, oops, sorry, let me change my pen back. It's going to be 2 e to the negative t times sine of t. And that's going to be the particular solution for the given initial conditions. Last little thing here, a couple of equations that are worth knowing. These just come up frequently, so they might just be worth recognizing them when you see them. These you can also just work them out by hand, so that's not a big deal, but the auxiliary equation for both of these is going to look like this. You're going to have r squared plus k squared is equal to 0, so the imaginary roots are going to be plus or minus ki, which means that alpha is 0 and beta is k, and so that means your general solution is going to be C1 cosine, because alpha is 0, so the e term goes away, C1 times cosine of kt plus C2 times sine of KT. And we'll talk a little bit more later about these sort of general forms for these and where those are coming from and how to generalize that. But for now, these might be a couple that just come up once in a while. So as an example, here's y double prime plus 9y equals 0. Notice it's in the format of that first equation. K squared is equal to 9, which of course means k is 3. So my roots are going to be plus and minus 3i, and my general solution is going to be c1 cosine of 3t plus c2 sine of 3t, and that's it. So that'll just save you a little bit of work of having to go through the entire auxiliary equation. All right, we will practice these tomorrow in class. Be sure to bring your notes with you, and I'll see you then.